I work at the Laboratory for Atmospheric and Space Physics, and I'm a part of the Atmospheric and Oceanic Sciences Department at this university. And I have the privilege of opening up this talk on how astrobiology pertains to exoplanets. And so what I've been doing for my project for the past several months, and what I hope to continue to do, is to take a look at the fairly common types of planets that we observe in the galaxy, or that we think we observe, and to assess how they might be habitable and under what conditions that might be true. So what I've been doing is I've been assessing the habitability of tidally locked Earth-like exoplanets around M-type stars. And as those are a lot of words, I'm going to explain more in depth what those mean and why we're interested in them. So first, you might ask, what is a tidally locked planet? I'm so glad you did. As explained by this excellent diagram right here, a tidally locked planet is a planet that always has the same side facing its star. So a great example of this is Earth's moon. We always see the same side of the moon, and it wasn't until we sent astronauts up that we got to look at the dark side of the moon. And why are we interested in this type of planet? We're interested in this type of planet because, according to certain surveys, some more, some less, tidally locked planets may make up for about half of the planets we observe out there. So some of those planets, perhaps half of those planets, maybe more, maybe less, might not actually be rotating. And a lot of studies have been done concerning how habitability pertains to Earth-like planets that rotate. So if we're going to expand our knowledge of what type of planets might be habitable, we need to take a look at these planets. Secondly, an M-star. So for the non-astronomers in the room, an M-star is a main sequence star that's the most common star in our galaxy. It's slightly cooler than our sun, and because of the fact that it's highly abundant, we need to know how this sort of star, its radiation, the planets that orbit it, might affect the habitability of these planets. So taken together, a tidally locked planet and M-stars, these types of planets are fairly common relative to others, at least in the terrestrial type planets, in our galaxy. And those are ideal candidates for studying habitability simply because they're fairly common and because a lot of studies give evidence that they might be common in general. And Earth-like. So I'm sure many people in this room would agree that there are many ways a planet might become habitable, and that is very interesting. For our purposes, however, we're trying to determine how a planet might stay habitable in the long term. So we're not going to theorize necessarily how a planet might become habitable, but whether that habitability is maintained. So what we did for our project is we simply took Earth as it is, stuck it around an M-star, made it tidally locked, and ran it and see what happens. And when I say Earth-like, I simply mean the planet has Earth's atmosphere, its mass, its composition, which include ocean and continental configuration, and the solar constant at the top of the atmosphere, so the irradiance received at the top of the atmosphere. All right, so how are we doing this? To do this, we've been using a very effective and very powerful GCM, which stands for General Circulation Model, called the Community Earth Systems Model, which was developed here in Boulder at the National Center for Atmospheric Research, NCAR. And what this model does is it's a 3D model which couples the various processes you might find on a planet's surface. So for instance, it takes the atmospheric processes, the oceanic processes, the land, sea ice, land ice processes. It analyzes their dynamics individually, the radiative transfer processes individually. It couples them, measures them together, and then after running the simulation for a certain amount of time, you get a snapshot of what the planet's going to be like in a couple of years, or several decades, depending on the scale. And for our specific purposes, we're also looking at a very powerful component of this GCM, which is the Whole Atmosphere Community Climate Model, abbreviated WACOM. And what this model does is it extends the atmosphere all the way up past 150 kilometers and allows for complex interactions between the different layers of the atmosphere. So it allows for communication, for example, between the mesosphere and the stratosphere. It analyzes the chemical constituents of the different components of the atmosphere, the radiative transfer processes. And we're very interested in that because we're looking into things like how the planet might be properly shielded from UV radiation, how the planet might what those chemicals might do to influence the planet's radiation budget. So we want to know the very intricate and specific components of the different spheres and how that will contribute to planetary habitability. And it's been very successful. The only problem, however, is that this is specifically geared to Earth. So it's a hell of a pain to adjust it for a different type of planet. Nevertheless, this has been our plan thus far. We have these GCMs. We have these powerful GCMs, CESM and WACOM. And we start off with our basic simulation of a rotating Earth around our sun. Step one of the plan has been to make Earth tidally locked. So this simply involves just altering the code such that Earth's day is equal to Earth's year. So we have the same side of the Earth facing the sun. run that, ensure it remains habitable, and if that is successful, we move on to step 2, which is to adjust the radiation spectrum received at the top of the atmosphere. For an M star, we move it closer to the planet such that it has the same solar constant at the, for this particular planet, and we ensure that it's tidally locked. And run it and see if it works. Just to give you an idea of what changing the radiation spectrum involves, the more complicated step is, I'm sure many of you are familiar with the Planck function. Here you can see the solar spectrum of the Earth at, according to different wavelengths. If we fit a Planck function to the sun, that coincides exactly with those observations. But with an M star, we're looking at peak wavelengths at different, peak radiances at different wavelengths. And so that's a bit more of a complicated process. All right, so due to the complicated nature of this project, we've only been able to do step 1, and I assure you we are very close to doing step 2, but not today. We've been able to do step 1, which is we've simulated 80 years of a current Earth, so Earth as it is, and we've also simulated 80 years worth of a tidally locked Earth. And these planets, very fortunately, are in equilibrium, radiative transfer equilibrium, and we're comparing them to make sure that current Earth is habitable. By God, we hope that's true. And that tidally locked Earth will remain habitable. To look for this, what we're looking for specifically is we're looking for adequate ozone shielding. So adequate shielding against harmful UV radiation that might destroy life before it can get off. Habitable temperatures such that the planet is comfortable at the surface, life can exist. And along with that is presence of liquid water. So we have results. Our first result, ozone distribution. So what you're looking at here on the left is current Earth ozone distribution. You're seeing a longitudinally averaged column ozone as a function of pressure, i.e. altitude, and latitude on the planet. And on the right, you're seeing the same thing for tidally locked Earth, except I will point out that for current Earth, this snapshot is the same regardless of which longitude specifically you're looking at. Tidally locked Earth, however, it's very different from the day and night side. We're very interested in the sun, in the day side, however, because that's the portion that needs to be shielded from the sun. So when we're looking at ozone concentration, and on Earth, most of our ozone is concentrated in the stratosphere, and that can reach up to 10 parts per million. So fortunately, we're able to simulate this for current Earth. We have up to 10 parts per million in the stratosphere, and it looks like those concentrations are there. That's what we observe normally with actual missions up to the stratosphere. And very fortunately, using the same scale, we have the same ozone concentration on our tidally locked planet. So it's very reasonable to conclude that this planet is adequately shielded from UV radiation. Brilliant. OK. And also going along with that is, in addition to ozone, an extra protection from the sun might be cloud cover. So what you're seeing here is you're seeing a map of the Earth centered around the prime meridian in the Pacific Ocean, and that's fairly typical cloud cover for Earth. On tidally locked Earth, however, all the clouds are concentrated over the substellar region, so right over where the sun is. So it's kind of cloudy where it is, but nevertheless, this is added protection against any additional radiation. Our second result is temperature. So again, what you're seeing is a slice of the atmosphere from longitudinally averaged slices across the planet. And fortunately, the two planets seem to have very similar temperature structures of the atmosphere. Of key importance is the temperature on the surface of the Earth. So we're looking at comfortable temperatures above freezing, above 273 Kelvin, but not 500. Fortunately, on the surface of our current Earth, that's what we observe, especially around the equatorial regions. And on our tidally locked planet, again, that's what we observe. So it's excellent. So we get to see that our tidally locked Earth is, in fact, comfortable above the substellar region, at least. This is not true for the entire planet. What you're seeing here for current Earth is that the temperature across the equatorial regions all the way up to the subpolar regions is fairly comfortable. You can have a jolly old time in any of the continents. But on the tidally locked planet, this comfortable temperature is only true over the substellar regions. So the entire planet is not necessarily habitable. Some of the continents might be covered in glaciers. But at least it is habitable for specific regions, which is still important. So the planet in general is still habitable regarding temperature. And finally, liquid water content. As I said, a lot of the planet might be covered in glaciers. I will admit for our current Earth simulations, it's a little bit colder. Earth might be going in a bit of an ice age right now, but Earth is still habitable. We have liquid water present, especially about the equatorial regions, and our tidally locked planet, it's right above the substellar region. And this is a map concerning ice cover as well. So the planet's not dry. It is, in fact, where there's not liquid water here, it's covered by ice. So liquid water is still there. Well, water is still there. It's just not necessarily liquid throughout the entire planet. All right, so from that very short presentation, what we've been able to conclude is that we have verified step one, that Earth that's tidally locked is not necessarily perfect, but it does remain habitable. This is because it does have that adequate UV shielding from ozone concentration that I mentioned, habitable temperatures on its surface, and it does have liquid water. So I'm no biologist, but I will say that those are pretty good components for having life on the surface of the planet. The next step will be to put it around an M star and see where that takes us. So I did end early, so I can take a couple of questions. Thank you very much. Oh, God.
Okay, Jay, you get the first one here.
Yeah, great talk. You pointed out, or rather, you were tidally locked over an ocean. Do you get any changes if you tidally lock over one of the continents?
That is a brilliant question, and I would love to give you an answer. We just haven't done it with the substellar region over the continents yet. So it's on the way, but I wish I could give you a better answer.
Okay.
I'm going to go over here first. I haven't been to this side of the room yet, sorry.
Hi, so my question is this is the Earth's atmosphere as it is now. So
Yes.
the Earth's atmosphere has not been the same over its lifetime.
That is very true.
With this code, can you change the composition of the Earth's atmosphere and see if you cranked up the carbon, what you would look like, and then track that through time?
We certainly can. There are many different components to this model. CSM has various, they're called comp sets, component sets, spanning pre-industrial revolution atmospheres, modern-day atmospheres. We just chose our current atmosphere because we had no reason not to. The atmosphere does evolve, that's absolutely true. We just so happen to start with this.
Hi, that was a great talk. Could you mind please going back to your temperature, that one?
Wait, this one?
This one,
Okay.
back one more, please.
Back.
That one.
Okay.
There you go. All right. So it looks like you're underestimating the fraction of ocean liquid. Can you tell me a little bit more about this, because you sort of went through this quickly?
Yes, I did. So what you're seeing here is you're seeing a map of Earth centered around the prime meridian, so around the Pacific Ocean. Mm-hmm. The red is fraction out of 1 of the surface covered by ocean, and the blue is not. But as I demonstrated from this subsequent plot, is that it's not necessarily dry, it's just covered by glacier. The model treats glacier and land to be the same. So,
okay, so you say glacier with it, so that's pack ice effectively? Is that how you would interpret that for modern? Is that basically, am I looking at pack ice in red for the modern ocean?
yes.
Okay, so your model actually effectively way underestimates the heat capacity of the ocean, or how the ocean atmosphere is reacting, right? So
Yes, this is obviously not current Earth.
no, I understand, but I'm wondering sort of that underestimation then gets transferred over to your scenario for the tidally locked Earth. In addition, do you take into account heat transport, latent heat transport by clouds?
The model should. I will say, however, that a possibility, one of the possibilities as to why this is true is it treats the ocean as a slab. It does not treat deep ocean dynamics, and that would be a very helpful step. It's just more computationally expensive. So since we did not output the ocean as we and this land and sea ice cover as we expect, that would be a very logical next step.
Hi. So when something becomes tidally locked, do you consider what happens to the magnetic field that it's generating? And if so, do you account for like the increased amount of flux that it's going to receive from the star from the wind?
We did not take that into consideration, no. I have no idea how the magnetic field would be affected.
We have time for one more quick.
Thanks. So back to the idea of M dwarfs, they're more active than solar-type stars. So would those tidal locked planets in the place where the enhanced UV radiation make a difference?
Yes, so they will be closer to their host star to consider if we're going to keep these irradiance at the top of the atmosphere constant. And yes, they are more active. There are a couple of papers out there that have analyzed solar flares and their effects on habitability. The latest one I read by, I think, it involved Dorian Abbott. He and his group did show that it was not as catastrophic as a solar flare from our sun might be, but that was specifically pertaining to UV shielding. So they looked at how it would affect ozone cover, and it only reduced it, I think, by 2% with a very powerful
I was wondering
flare.
for tidally locked planets, you might be able to push the habitable zone further out. Therefore, the UV radiation might not be as important. That's just a thought.
I would have to investigate further.
All right, let's thank Alex again. We have to move on.